Okay, so today I'm going to talk about the cohomology of Lie algebras and give a proof of the Levi decomposition, which is a result in Lie algebras. So I guess sort of the plan is to introduce, in general, the cohomology of Lie algebra, starting from some basic differential geometry. We'll introduce the Chevalley-Eilenberg complex, which is how we derive that cohomology. And yeah, from there, we'll state a result that we'll use in the proof of the Levi decomposition, which is Whitehead's lemmas, or Whitehead's theorem. And then we'll ultimately prove the Levi decomposition in full generality. And my proof is slightly based on Ettingoff's lecture notes on Lie algebras. He states it at the end of his lecture notes, and it's around 4 sentences, or maybe 5, I forget. It's very short and brief, so we use his approach, but vastly, I guess, lengthen it and fill in the details. He leaves quite a bit to question in his proof, so we'll spend maybe close to 30 minutes, 25 minutes on the proof of the Levi decomposition alone, fully fleshing it out in full generality, with some auxiliary proofs and lemmas along the way. So I think it'll be quite interesting. Like I mentioned, we'll start with the differential geometry aspect of it, which we'll get into now. So, sort of the basis for the algebras, studying the algebras, is starting from the application, which is Lie groups. Probably the best place to start when you study the algebras. And when we do so, we consider, some sort of Lie group, which is also a manifold, and some sort of action on this manifold. So in terms of differential geometry, you have these differential forms, and they form this chain complex of differential forms on the manifold. With the RAM differential between, of course, 0 here. And from this chain complex, we get the RAM cohomology. So, specifically, if we're looking at a manifold M with coefficients over the complex numbers, we'll just take the closed forms on M and mod out the exact forms. And this is just the usual definition of kernel mod image. Sorry for blocking the board. Yeah. So, there's kind of a lot to be said here. I could talk a bit about the Lie derivative and Cartan's magic formula. And we'll try not to get too hung up on the differential geometry details, just so that I can spend most of the time proving the Levi decomposition. So I'll kind of speed through these results. One interesting result, though, that will be of use for us is one that kind of follows from inspecting the averaging operator, sometimes known as P. I guess kind of heuristically, you have some object, and you have a vector field on M as well, and you're kind of looking at how this thing smears across the flow, or just some proof action in general. The defining property of the averaging operator is that composition is just P itself. But in any case, we use this guy to give quite an interesting result in terms of these differential forms, which is that if we have compact Lie group G acting on our manifold M, then we get this sort of decomposition of the differential forms on M, given by, and I'll flesh this out more in a second. I mean, like I said, I won't get too many details here at this state, but because really we want to kind of move quickly through this content, but this decomposition is quite nice. And specifically, this term here is exact. So when we take this and put it into our chain complex, because this term is exact, when we take the homology, it doesn't really matter at all, of course. So this is the only term remaining when we're actually computing homology. And I can kind of write this out, like what happens here, just so that it's maybe more clear. Essentially, if we started with this chain complex, maybe like this, I minus one of them, and then we have some differential I. P is essentially a chain map, is what I'm trying to get at. Suppose I could have just said that. My apologies. And like I mentioned, this term is exact. So down here, really, all we have is this guy. I'm not really sure if there's a name for him or not. I don't know. This one. So G up here as well. Chain map. And like I mentioned, this part is the only one that matters. These are the G invariant forms on M. So all that means is that G star omega is omega for any G in the group and some form omega, differential form omega. Yeah. What else do I want to say on this? These guys are the zero average forms. They're the ones that are exact. And of course, this P induces an isomorphism on homology, so that's why we can just ignore it. Okay. So I'll say this is a theorem. It's really not a theorem, more of a definition, but we can be pedantic. Doesn't matter. Essentially, the cohomology of a Lie group G with coefficients in C is computed, I'll write it out. It's computed as variable D by the chain complex of specifically G. So so we're replacing M with G here, and these are the left invariant differential forms. On G. Cool. So the complex of these guys is actually the Chevalley-Eilenberg complex. So Chevalley-Eilenberg complex is I can write it out, I guess. 0 G differential 1. And the differential here deserves its own sort of comments and remarks. So, what does it say about that? So, I guess just formulaically kind of recall the invariant form or invariant formulation of the exterior derivative, right? Essentially you have some differential form omega and you have some amount of a vector field in your manifold and you get this sum of two alternating sums, which is your exterior derivative. Now, what happens in our case is that there's these functions that look something like omega of one vector 3, and we we omit this guy, the ith vector field, and go on. These guys are actually constant when we consider omega to be a left invariant field, or sorry, a left invariant differential form. So these guys are some constant, like this. And so actually the first sum in that sum of two alternating sums actually vanishes. So what we're left with in terms of differential here is, maybe I'll say dn, just to denote, it's not in my notes, but yeah. Say dn of omega, a vector field 0, 1, this is just the alternating sum of just strictly i's less than j. So it's a -1, I plus j, and I think it's omega the commutator of vi, vj, and then we omit both of those fields. Yeah, I think it is this. I hope it's that. Yeah. So this is our differential here. And I won't write it out in full generality like this again, but just for reference, this is what we're using here. And we'll state it in the case specifically of D2 and D1 quite extensively, actually. So yeah, okay. I guess what else is there to say? Yeah, how do we go and extend this from the Lie group case to the Lie algebraic case, right? That's probably a good question to ask at this point. And it has nothing to do with the differential, I just want to specify that. So I guess I'll start over here. Well, specifically, if we have a Lie group G, and we take its Lie algebra, something like this. Yeah, then these left invariant differential forms are actually isomorphic to, where is it? Yes, the wedge product of these G's. Now, okay, it's notationally it's probably not a good idea. Yes. It should be like this. Yeah. So I'll stop using star for arbitrary index because now star will be the dual. But we have this isomorphism, and so essentially what we do here is very straightforward. As a corollary of this proposition, it's quite immediate, and it's how we define Lie algebra cohomology. Essentially, we just apply. And I can prove this. I'm not going to. The proof is quite straightforward. You use the fact that the differential forms are left invariant, and you use the fact also that the differential forms at any element in the group are simply defined by their behavior at the identity. And then you just construct your forward map using that knowledge, and then actually it's the same thing going backwards. You use the left invariance. I think you also use symmetry and maybe sorry, not symmetry, alternating, and the fact that it's smooth. That's just the Sparks Note version of that. But okay, yeah, so essentially the corollary here is you have Lie group G, and the algebra G, C, then yeah, I mean, all we're going to basically do is substitute this isomorphism into the chain complex, and we get the following. So, sorry, 0 wedge of G. We take the dual, and we just go from there. So, 1, 2. I mean, yeah, and these two terms specifically, this is just C, this is just G dual. Maybe it's also worth mentioning that if G is finite dimensional, then you can just pull the dual into the wedge product. Sorry, yeah, into the wedge, and so it just becomes, you know, the nth wedge of G dual. Again, specifically for G finite dimensional. And yeah, so this chain complex with the aforementioned differential is the Chevalley-Eilenberg complex of a Lie algebra G. Yeah, I mean, in previous discussion, we kind of assumed that G, the Lie group G, was compact. It's not entirely necessary in full generality, to be honest. Also, sorry if this is off screen. My apologies. I don't think it should be. But yeah, and so we'll denote the homology of this guy as, I don't know where to put this, maybe here, is CE of G. And like I mentioned, the cohomology of the Lie algebra G follows from taking the homology of this guy. Yeah, and you know, maybe you want arbitrary coefficients, probably want arbitrary coefficients. So what do you do in that case? I mean, it's not enough to just say, oh, it's the homology of that sequence, or sorry, cohomology of that sequence. I mean, it is, but you know, more rigorously, we'll define, you know, the Chevy. Sorry. Well, yeah. So the Chevalley-Eilenberg complex of the Lie algebra G with coefficients in V. V here being a G module. A G module. You can define it as, you know, morphisms from N, G to V. Sorry, this should be, I mean, I'm going to stop using this notation, but yeah. Like that. And, I mean, this is isomorphic to maybe a definition that's more familiar is, you know, n wedges of G dual, and then you tensor product your coefficient module. I mean, this is the same thing that's done in homology. So yeah, I mean, there's some other comments I can make as well. When V is specifically finite dimensional, you can express it differently and use the diagram differential. Honestly, I will leave this and state the result of the hour. Not actually, the result of the hour is Levi decomposition. This is the second result of the hour, I don't know. It is Whitehead's theorem. Whitehead, yeah. So if your Lie algebra is semi-simple, and V is a G module, then the first cohomology and the second cohomology both vanish. Wonderful result. Yeah, okay, so I should mention that I originally wrote this talk for my undergraduate presentation in Lie Algebras class, and in that talk I also proved this result, specifically in the case of H2, because we proved H1 in class, and the proof is not necessarily short. What can I say about it? I mean, yeah, the proof, the only standard way I know of proving it is to construct a Casimir element, and then you take a cocycle and show that it's a coboundary force, right? What else can I make? Comments as, yeah, there's kind of two cases you have to inspect as well. One where the Casimir element acts trivially, so C is 0, and then one where it doesn't, so C is non-zero. And I mean, there's two standard arguments used for both. It's sort of a trick. I mean, I can make a separate video on it. It's not remarkable in my opinion. But yeah, like I mentioned, in both cases, you just use a Casimir element. And specifically, I think, in the case where the Casimir element acts trivially, you consider G dual to be a dual representation. So it's a G module, and yeah, it's a dual representation. So every two form automatically has this nice one form. Okay, I'll stop yapping about Whitehead's theorem. The point is that it's a beautiful result. Both of the first two cohomologies vanish. And even stronger than this, actually, is that if V has no, I think it's if V has no invariant elements, all of the cohomologies vanish, which is pretty cool. I don't have this specifically in my talk. It's something like that. Source, trust me, bro. So yeah, okay. Some comments on Whitehead's theorem is that you can actually get a lot of really fruitful results from this result alone. I mean, I have some examples in my talk specifically for H0, H1, and H2. Maybe I'll make quick remarks on these. This is quite easy. So, I mean, the first example is to consider something like H0. I mean, the zeroth cohomology of this guy is just the G invariance of V. The G invariance in V. What else is there to say? Yeah, I mean, let's see. This eraser sucks. I mean, my example for H1 just has me defining, not just defining, but I mean, the only useful part is that it defines the first differential of a differential form, but that'll come up later in the talk. Yeah, I mean, I guess there's some intuition about the formula for it. Yeah, maybe another remark I can make on specifically the first cohomology is that these one cocycles, they actually represent all the derivations. They're actually so okay. It's a Lie algebra of the derivations of G. Pretty cool. What's cooler though is that the one coboundaries, this guy is a, I don't know if ever, yeah, oh, yeah, it's actually an ideal, it's even cooler, of the inner derivations. Of course, what you're left with in the first cohomology, when you mod out by these guys, and you take out these inner derivations, are obviously the outer derivations. So yeah, H1 classifies all the outer derivations of your Lie algebra. Of course, Whitehead's theorem only holds when your Lie algebra is semi-simple. So heuristically what happens is that when your Lie algebra is semi-simple, then all the derivations of a semi-simple Lie algebra are inner. Yeah. Okay, nothing remarkable going on now. The remarkable part, I guess, happens at H2. I won't go too much into the result, but you can show if you have, I guess if you have an abelian extension of G, H2, the second cohomology classifies all these guys. So again, that means if G is semi-simple, all of your abelian extensions are classified by the vanishing second cohomology. That's pretty cool. I mean, the proof of this is kind of just going to be a waste of our time. But yeah, it classifies all of the abelian extensions modulo, up to isomorphism essentially. Specifically, I think isomorphisms that act trivially on both B and G. Yeah. So it's measuring the obstruction specifically to making extensions split. Actually, early in our class, that's how we defined the first cohomology was by extensions. Yeah, nothing too long. Okay. Without further ado, let's just get into the heart of the talk. Levi decomposition. The proof is going to be a bit long, so buckle your seatbelts. Levi decomposition.